We would like to look at the average velocity on a position versus time graph from another perspective. Here we have Ophelia's motion once again as she blunders about the castle. And if I want the average velocity between events D and E, I know I need the displacement over the time interval. So I've drawn in the displacement here, delta x, that vertical line, and this horizontal line indicating the time interval between D and E, delta t. And I've also drawn a dotted line connecting these two events. The dotted line is very close to the line of her actual motion, not exactly on it. But now when you see this triangle here, it should look familiar. It should look like something you've seen in math class. It should look like the kind of thing you would draw if you were going to attempt to calculate the slope of this dotted line. In that context, delta x, our displacement, which we can tell is 24 meters here, looks like the rise that you would calculate when finding the slope. Our delta x is our rise. Likewise, the time interval, delta t, 3 seconds, that looks like our run. So delta x over delta t, which works out to 8 meters per second, is exactly the same calculation we would do if we were trying to find the slope of that connecting line. Slope of the line connecting those two events, D to E. Which brings us to one of our key concepts in kinematics. On a position versus time graph, the slope of a line connecting any two events, such as these, the slope of the line connecting those two events, is exactly equal to the average velocity between those two events. Because we define average velocity as displacement over time interval, as the rise over the run, we're defining average velocity to be identical to the slope of that connecting line. Let's look at another example from this graph. How about the average velocity between events D and F? I can draw in another triangle. Here will be the delta x, our rise between D and F. And this horizontal line will be our run, delta t. And I'll draw a dotted line in connecting D to F, connecting these two events. So now when I'm calculating the average velocity between those two events, what I'm doing is taking the rise over the run. Our delta x is again 24 meters, but our run now, our time interval, is 5 seconds. Here's our rise, up 24 meters, or 24 meters in the positive direction, I should say, and then our run 5 seconds forward in time. 24 over 5 gives us about 4.8 meters per second. And that value we just calculated is exactly the slope of that dotted line connecting those two events. Slope of the line connecting D to F. Okay, from D to E, the slope is 8 meters per second. From D to F, it's 4.8 meters per second, so it's steeper. We see that this line here is steeper than this line, which is a shallower slope. In other words, our average velocity is greater from D to E than from D to F. And we can see why that is. When we're getting the average velocity from D to E, we're finding the average velocity while she's moving in the positive x direction. But then if we're finding the average velocity from D to F, we're including this part of the velocity, but we're also averaging in this period where she's not moving at all, where her velocity is 0. So we average in this positive velocity with this 0, we get a smaller value, 4.8 meters per second. How about let's look at average velocity from E to F, from here to here, that horizontal line right there. Well, you know that our delta x is 0 right here, our rise is 0, we haven't gone up or down at all, 0 meters over 2 seconds. So we're not moving there at all. Our velocity is 0 meters per second. 0, which is the slope of a horizontal line. Slope of a horizontal line. When an object is stationary, when it's not moving, its motion on a position versus time graph is a horizontal line, the slope of which is 0. Therefore, the average velocity is 0. Two more. Let's look at from B to C and from F to G. From B to C, I can draw in a delta x and a delta t, and my dotted line connecting them. From F to G, there's a delta x. Oh, sorry, that's a delta t. There's a delta x. It's okay to draw a triangle upside down, same thing. And then a dotted line connecting those two events from F to G. So without doing any calculations, I can look at the slopes of these two lines to get some idea of the average velocity between these two events and the average velocity between these two events. You can tell by eyeball that this slope is a bit steeper than this slope. This slope here, if I bring it over, I realize, aha, I've got to tip this way to match that slope. That's a more shallow slope right there than this one right here, which tells me that I have a greater velocity in the negative direction between F and G than I do in the negative direction between B and C. So this is going to work out to be a more negative slope than this one. And we do the calculation to see that that is indeed the case. From B to C, the slope is negative 2 meters per second. From F to G, the slope is negative 4 meters per second. So in this way, we connect the slope of the line connecting two points with the average velocity between those 2 points. For some exercises, take a look at this other motion graph for some other object. And pause the video for a moment and answer this. Between which two events on this position versus time graph does the object have the greatest positive average velocity? And between which two events does it have the greatest negative average velocity? And I want you to think about what we've just learned in terms of slope of a line connecting these 2 points to come up with this answer. Ready? From A to B, greatest positive velocity, and from, let's see, I can draw in that connecting line right there. That's a very large positive slope. And from E to F, that's a very large negative slope. Large positive velocity, large positive slope, large negative velocity, large negative slope. A couple more questions. How does the average velocity from C to D compare to the average velocity from G to H? Also, how does the average velocity from C to E compare to the average velocity from F to H? Pause the video, think on that for a moment. Ready? From C to D, we can draw in that dotted line. From G to H, we can draw in that dotted line. We can compare the slopes of these two lines, and by eye, you can see that the slope of this is 1 meter per second. It's going up over 1, up 1, over 1, up 1, over 1, up 1. Same thing here, over 1, up 1, over 1, up 1. They have identical slopes, therefore the average velocities are identical. They're the same, 1 meter per second each. Average velocities from C to E. Let's draw in that dotted line. And from F to H. drawing that line. And again, from I, you can see that this one is more steep upwards than this one. That's a steeper positive slope than this one, which is tilted down a little flatter. You can do the calculation to verify. From C to E, your rise is 5 over 8. 0.6 meters per second is your slope. From F to H, 0.5 meters per second, up to over 4.